Come on. Evet. Nasılsınız gençlik? İyi misiniz? Are you getting ready for the midterm? Okay. So, next week. We will have an exercise session. It's 30. And the midterm is later in the evening. Midterm. I think it was what? 18 o'clock, right? So if you have any questions, okay, let me do this also on Zoom. There are only how many? 4. And you are about 6, 10, 12, 13, 14. All right. So let me put it into chat. Next week, we are having exercise session at 12:30. Midterm at 18 o'clock. If you have any problems, questions, and so on, this might be a good chance to discuss it before the midterm. So it will be like double class. Do you have any questions regarding the copy sheet and so on? Is everyone familiar with the copy sheet? Remember? You are going to have an A4 size, like this size, sheet, both sides. You can write anything you want that would be useful for the exam, so all the formula and so on. And you don't have to memorize any equations or something like that. The only thing you need to do will be doing calculations or doing some analysis, like we do in the exercise session. So you are okay with that? And it's going to be an interesting, very interesting face-to-face midterm. And I guess now I see only a few of you. Then I will see the whole class. And I hope it's good for both you and us, because at least you can ask questions like right here, face to face, or you can also during the lectures, just basically interrupt me and ask questions. I don't mind, because mostly there are 1 or 2 of you who ask questions and the other ones just listen. And in fact, how do you take notes? Do you take notes or do you listen to the recording? How does it work with you? Oh, so you take the notes later. Okay. I was just wondering because you certainly are a different generation and your methods of working or learning something is quite different than our methods. We are sort of dinosaurs and probably according to you, we are old fashioned, even though I'm only 58. So anyway, any questions? Yeah, bring your scientific calculator. Yeah, please. Everybody should bring a calculator. Okay, I should write this down here. Please bring your own scientific calculator. Any other questions? Okay, in that case, we'll start directly with the slides. And of course, I need to connect this, right? Without connecting, neither you nor the others will be able to watch. All right. So, hello. Here we are. All right. So it's already 6th week. And that means do you know how many weeks a semester is? 14. So 6 means we're almost halfway there. So time flies. Time really flies. I do also have some videos for you. But before going into the videos, I think we should at least first watch or go over, hello. Okay, go over some of the things and then we'll watch the videos and it will probably make more sense. So, you know, now every week before I start, I give like a brief overview of what we did the previous week or the previous weeks. So this again is now the 3-pin semiconductor device, this so-called bipolar junction transistor or BJT. The BJT, let me get my pointer. The BJT, the discrete BJT looks like this. It's about a centimeter or so long with the pins and so on. Guys, would you mind closing the door? Thank you. Thanks very much. So it's either shown like this, symbolically, or like that. And but this is like a more structural representation of it. So up here we see the n plus pn. Down here we see p plus np, and you remember why I call it p plus or n plus, right? Because the emitter of either is heavily doped when compared to the collector. An emitter and collector are of the same kind. Either they're both p or both n, and in between sandwiched is the base region, which is very, very thin. You remember why it's thin? Let's call them charge carriers. They can, yes, what? And they can go through without being recombined and annihilated. Some do. And so we have contacts to these 3 regions, and the pins are connected to that to those contacts. In the symbolic representation, the arrow indicates where the emitter is, meaning the p plus or n plus side. So this is n plus pn, the arrow goes out. This is p plus np, the arrow goes in, and it's upside down, you see. And so in the active mode, which is used for amplification. And in this class, although we saw some on-off switch mode or logic gates in the exercise session, we are going to be mainly involved with amplifiers and how we can build amplifiers. So you remember the emitter current is equal to the sum of the base and collector currents. And the collector current can be represented in terms of the base emitter voltage, like a diode, right? It's a nonlinear device. And the IS is the saturation current or the dark current. And it can be as small as femtoamperes. Femto is 10 to the power of minus 15. And beta or HFE is the current gain, meaning the ratio of collector current to base current, because the base current, which is actually a very small current, controls the collector current. So the operation, remember, one junction is forward biased, the other one is reverse biased. So the junction, base emitter junction, is always forward biased, like a diode. And the other junction, yeah, please come in. All right, ladies. So the base emitter junction is forward biased so that the emitter can inject charged carriers, and in this case, P plus and P, meaning holes, into the base, but the base should be thin so that the holes should not combine with the majority carriers of the base, that are the electrons. And then the reverse biased collector base junction, basically with the help of the depletion zone, pulls the holes from the base region into the collector region. And although the input characteristic looks like this, and multiplied by beta is the collector current, basically, the output characteristic is a family of curves. And when in active mode, the base emitter junction is biased with something like 600, 700 millivolts. The collector emitter junction, at least for this class, as long as it's the collector base junction is reverse biased, we don't care how high the collector emitter voltage is. So the minimum of the collector emitter voltage should be equal to VBE. In that case, the collector base biasing is 0 volts, and 0 basically means there is a depletion zone. Now we are going to get familiarized with something that is important. You remember I asked you in one of the first classes why computers and many electronic devices have a fan? Remember anyone? Or why do devices, semiconductor electronic devices, get hot or warm? Like if you talk on your cell phone for a long time, you realize, and even if you touch your ear, that your ear gets hot, right? Or at least warm. And why is that? There is a hint here. And what is that hint? It says maximum power hyperbola. So basically, the area under the curve represents the maximum power. What is the maximum power? Maximum power in electrical terms is the multiplication of current and voltage, right? semiconductor devices, like also engines and so on, when a current passes, get warm. So there is a maximum current and voltage or power that you can use your semiconductor device at. And let's, for example, 10 milliwatts, right? So in terms of current and voltage, 10 milliwatts would be under this curve. So if you are working at a voltage of 5 volts, 10 milliwatts would require that your current should not be any higher than how many milliamperes? Simple math, guys. How many? I mean, do you understand it, or I'm expecting some sort of reaction? Okay, I'll repeat the question. If a device is designed to work at a maximum power of 10 milliwatts, if the voltage it is operating at is around 5 volts, how many milliamperes is the maximum current? 2, right? So you need to work under this curve. You shouldn't have any current any higher than 2 milliamperes. So you should adjust like all your biasing resistors and so on, so that, for example, your collector current never goes above 2 milliamperes. So that's the importance of the maximum power hyperbola. And if you go over the curve, then your device and transistors, when they get hot, they basically explode big time. So you have to be careful. And having said that, now I would like to show you the video, and it's still showing. Hello. I stopped sharing. However, okay. Now, what was that? Windows P? To get back here, Windows P. Hello. All right, come on. Okay. Now we are going to watch a video. Let me go back to Zoom. And transistors explained. Share sound. And let's see. It's about 18 minutes, but it's a very nice one. Hopefully you would like it.
In many shapes and sizes. Transistors are small electronic components with 2 main functions. It can act as a switch to control circuits, and they can also amplify signals. Small, low-power transistors are enclosed in a resin case to help protect the internal parts, but higher power transistors will have a partly metal case, which is used to help remove the heat which is generated, as this will damage the components over time. We usually find these metal body transistors attached to a heatsink, which helps remove the unwanted heat. For example, inside this DC, we have some MOSFET transistors which are attached to very large heat sinks. Without the heatsink, the components quickly reach 45 degrees Celsius, or 113 degrees Fahrenheit, with a current of just 1.2 amps. They will become much hotter as the current increases. But for electronic circuits with small currents, we can just use these resin body transistors, which do not require a heatsink. On the body of the transistor, we find some text. This will tell us the part number, which we can use to find the manufacturer's datasheet. Each transistor is rated to handle a certain voltage and current, so it's important to check these sheets. Now, with a transistor, we have 3 pins, labeled E, B, and C. This stands for the emitter, the base, and the collector. Typically, with these resin body type transistors with a flat edge, the left pin is the emitter, the middle is the base, and the right side is the collector. However, not all transistors use this configuration, so do check the manufacturer's datasheet. We know that if we connect a light bulb to a battery, it will illuminate. We can install a switch into the circuit and control the light by interrupting the power supply. But this requires a human to manually control the switch. So how can we automate this? For that, we use a transistor. This transistor is blocking the flow of current, so the light is off. But if we provide a small voltage to the base pin in the middle, it causes the transistor to start allowing current to flow in the main circuit. So the light turns on. We can then place a switch on the controlling pin to operate it remotely, or we can place a sensor on this to automate the control. Typically, we need to apply at least 0.6 to 0.7 volts to the base pin for the transistor to turn on. For example, this simple transistor circuit has a red LED and a 9-volt power supply across the main circuit. The base pin is connected to the DC bench power supply. The circuit diagram looks like this. When the supply voltage to the base pin is 0.5 volts, the transistor is off, so the LED is also off. At 0.6 volts, the transistor is on, but not fully. The LED is dim because the transistor is not yet letting the full current flow through the main circuit. Then, at 0.7 volts, the LED is brighter because the transistor is letting almost the full current through. And at 0.8 volts, the LED is at full brightness. The transistor is fully open. So what's happening is we're using a small voltage and current to control a larger voltage and current. We saw that a small change to the voltage on the base pin causes a large change on the main circuit. Therefore, if we input a signal to the base pin, the transistor acts as an amplifier. We could connect a microphone which varies the voltage signal on the base pin, and this will amplify a speaker in the main circuit to form a very basic amplifier. Typically, there is a very small current on the base pin, perhaps just 1 milliamps or even less. The collector has a much higher current, for example 100 milliamps. The ratio between these two is known as the current gain and uses the symbol beta. We can find the ratio in the manufacturer's datasheet. In this example, the collector current is 100 milliamps and the base current is 1 milliamp. So the ratio is 100 divided by 1, which gives us 100. We can also rearrange this formula to find the currents also. We have two main types of bipolar transistors, the N and P type. The two transistors look nearly identical, so we need to check the part number to tell which is which. The N transistor, we have the main circuit. Both are connected to the positive of the battery. The main circuit is off until we press on the control circuit. We can see both wires to the transistor. We can remove the main circuit and the control circuit LED.
Excuse us, the ones in Zoom? Yes. if you have for example, a resistor, only whatever 600, 700 millivolts will drop between base and emitter, and the rest will drop on the let's say resistor. So the transistor or the base emitter junction adjusts itself if there is a resistor on which the rest of the voltage might drop. Make sense? Okay. Now, let's restart, not restart, start. All right, the question was, what if a larger voltage is applied? And the answer is if there is a resistor, oops, okay, here we go. If there is a resistor, the rest of the voltage drops on that resistor. So here we go.
N and the PNP type. The two transistors look nearly identical, so we need to check the part number to tell which is which. With an NPN transistor, we have the main circuit and the control circuit. Both are connected to the positive of the battery. The main circuit is off until we press the switch on the control circuit. We can see the current is flowing through both wires to the transistor. We can remove the main circuit, and the control circuit LED will still turn on when the switch is pressed, as the current is returning to the battery through the transistor. In this simplified example, when the switch is pressed, there are 5 milliamps flowing into the base pin. There are 20 milliamps flowing into the collector pin, and 20 the positive of the battery. The main circuit is up until we press the switch on the control circuit. We can see with this type that some of the current flows out of the base pin and returns to the battery. The rest of the current flows through the transistor and through the main LED and then back to the battery. If we remove the main circuit, the control circuit LED will still turn on. In this example, when the switch is pressed, there are 25 milliamps flowing into the emitter, 20 milliamps flowing out of the collector, and 5 milliamps flowing out of the base. The current therefore divides in this transistor. I'll place these side by side so you can see how they compare. Transistors are shown on electrical drawings with symbols like these. The arrow is placed on the emitter. The arrow points in the direction of conventional current, so that we know how to connect them into our circuits. To understand how a transistor works, I want you to first imagine water flowing through a pipe. It flows freely through the pipe until we block it with a disc. Now, if we connect a smaller pipe into the main one and place a swing gate within this small pipe, we can move the disc using a pulley. The further the swing gate opens, the more water is allowed to flow in the main pipe. The swing gate is a little heavy, so a small amount of water won't be enough to. A certain amount of water is required to force. The more water we have flowing in this small pipe, the further the valve opens and allows more and more water to flow in the main pipe. This is essentially how an NPN transistor works. You might already know that when we design electronic circuits, we use conventional current. So in this NPN transistor circuit, we assume that the current is flowing from the battery's positive into both the collector and the base pin, and then out of the emitter pin. We always use this direction to design our circuits. However, that's not what's actually occurring. In reality, the electrons are flowing from the negative to the positive of the battery. This was proved by Joseph Thomson, who carried out some experiments to discover the electron and also proved they flowed in the opposite direction. So, in reality, electrons flow from the negative into the emitter and then out of the collector and the base pin. We call this electron flow. I'll place these side by side so you can see the difference in the two theories. Remember, we always design circuits using the conventional current method. But scientists and engineers know that electron flow is how it actually works. By the way, we have also covered how a battery works in detail in our previous video. Do check that out, links can be found in the video description down below. Okay, so we know that electricity is the flow of electrons through a wire. The copper wire is the conductor and the rubber is the insulator. Electrons can flow easily through the copper, but they can't flow through the rubber insulator. If we look at this basic model of an atom of a metal conductor, we have the nucleus at the center, and this is surrounded by a number of orbital shells which hold the electrons. Each shell holds a maximum number of electrons, and an electron needs to have a certain amount of energy to be accepted into each shell. The electrons located furthest away from the nucleus hold the most energy. The outermost shell is known as the valence shell. A conductor has between 1 and 3 electrons in its valence shell. The electrons are held in place by the nucleus. But there is another shell known as the conduction band. If an electron can reach this, then it can break free from the atom and move to other atoms. With a metal atom, such as copper, the valence shell and the conduction band overlap, so it's very easy for the electrons to move. With an insulator, the outermost shell is packed. There's very little to no room for an electron to join. The nucleus has a tight grip on the electrons, and the conduction band is far away, so the electrons can't reach this to escape. Therefore, electricity cannot flow through this material. However, there's another material known as a semiconductor. Silicon is an example of a semiconductor. With this material, there's one too many electrons in the valence shell for it to be a conductor, so it acts as an insulator. But as the conduction band is quite close, if we provide some external energy, some electrons will gain enough energy to make the jump into the conduction band and become free. Therefore, this material can act as both an insulator and a conductor. Pure silicon has almost no free electrons. So what engineers do is dope the silicon with a small amount of another material, which changes its electrical properties. We call this p-type and n-type doping. We combine these materials to form the p-n junction. We can sandwich these together to form an NPN or a PNP transistor. Inside the transistor, we have the collector pin and the emitter pin. Between these, in an NPN transistor, we have 2 layers of n-type material and 1 layer of p-type. The base wire is connected to the p-type layer. In a PNP transistor, this is just configured the opposite way. The entire thing is enclosed in a resin to protect the internal materials. Let's imagine that the silicon hasn't been doped yet, so it's just pure silicon inside. Each silicon atom is surrounded by 4 other silicon atoms. Each atom wants 8 electrons in its valence shell, but the silicon atoms only have 4 electrons in their valence shell. So they sneakily share an electron with their neighboring atom to get the 8 they desire. This is known as covalent bonding. When we add the n-type material, such as phosphorus, it will take the position of some of the silicon atoms. The phosphorus atoms have 5 electrons in their valence shell. So, as the silicon atoms are sharing electrons to get their desired 8, they don't need this extra one, which means there's now extra electrons in the material and these are free to move around. With p-type doping, we add in a material such as aluminium or aluminum. This atom has only 3 electrons in its valence shell. It therefore can't provide its 4 neighbors with an electron to share, so one of them will have to go without. This means a hole has been created where an electron can sit and occupy. We now have 2 doped pieces of silicon, one with too many electrons and one with not enough electrons. The 2 materials join to form a p-n junction. At this junction, we get what's known as a depletion region. In this region, some of the excess electrons from the N side will move over to occupy the holes in the P side. This migration will form a barrier with a buildup of electrons and holes on opposite sides. The electrons are negatively charged, and the holes are therefore considered positively charged. So this buildup causes a slightly negatively charged region and a slightly positively charged region. This creates an electric field and prevents more electrons from moving across. The potential difference across this region is typically around 0.7 volts. When we connect a voltage source across the two ends, with the positive connected to the p-type material, this will create a forward bias, and the electrons will begin to flow. The voltage source has to be greater than the 0.7 volt barrier, otherwise electrons cannot make the jump. When we reverse the power supply, so that the positive is connected to the N-type material, the electrons held in the barrier will be pulled back towards the positive terminal and the holes will be pulled back towards the negative terminal. This has caused a reverse bias. In a NPN transistor, we have two layers of N-type material. So we have two junctions and therefore two barriers, so no current can flow through it ordinarily. The emitter N-type material is heavily doped, so there are a lot of excess electrons here. The base P-type is lightly doped, so there are a few holes here. The collector N-type is moderately doped, so there are a few excess electrons here. If we connect a battery across the base and the emitter, with the positive connected to the P-type layer, this will create a forward bias. The forward bias causes the barrier to collapse as long as the voltage is at least 0.7 volts. So the barrier diminishes and the electrons rush across to fill the space within the P-type material. Some of these electrons will occupy a hole, and they will be pulled towards the positive terminal of the battery. The P-type layer is thin and was lightly doped on purpose, so that there is a low chance of electrons falling into a hole. The rest will remain free to move around the material. Therefore, only a small current will flow out of the base pin, leaving an excess of electrons now in the P-type material. If we then connect another battery between the emitter and the collector, with the positive connected to the collector, the negatively charged electrons within the collector will be drawn to the positive terminal, which causes a reverse bias. If you remember, with the reverse bias, the electrons and holes of the barrier are pulled back across. So the electrons on the P-type side of the barrier are pulled across to the N-type side, and the holes on the N-type side are pulled back to the P-type side. There are already an excess number of electrons in the P-type material, so they will move to occupy these holes, and some of them will be pulled across, because the voltage of this battery is greater, so the attraction is much higher. As these electrons are pulled across, they flow into the battery, so a current develops across the reverse bias junction. A higher voltage on the base pin fully opens the transistor, which means more current and more electrons moving into the P-type layer. Therefore, more electrons are pulled across the reverse bias. We also see more electrons flowing in the emitter side of the transistor compared to the collector side. Okay, that's it for this video, but to continue learning about electronics engineering, click on one of the videos on screen now.
So I hope things are a bit clearer now, right? And so let's move back to the slides. And I was probably here on this slide, right? Yeah. So we need to stay under the maximum, where's my pointer? Under the maximum power hyperbola. So without the emphasis, this is the output characteristic of the transistor. The input was between the base and the emitter. The output is between the collector and the emitter. And the input power is, let's say, 500, 600, 700 millivolts multiplied by the base current. And the output power is, let's say, 5 volts multiplied by the collector current. The collector current is at least 100 times higher than the base current. So we can assume that the output power is almost equal, the total power is almost equal to the output power. And so if we have to stay under a certain power, then we need to take into account the maximum power hyperbola and try to stay under this. Or like you saw in the video, you might have to use heat sinks or fans to be able to draw larger currents. We also learned about the early effect last week and the different modes of operation. If I need to recap this and make it a little bit visually appealing, this is a transistor. The base emitter is forward bias, and the collector is connected to a VCC, which is anywhere from 5 to 7 to 15 volts. And a biasing resistor is connected here to adjust the collector and thus the base current, because there is no connected to the base, as you see. So what is the output voltage like? And let's say the output is from the collector of this transistor. So the range of output voltages is anywhere from VCC, which is the power supply, down to about several hundred millivolts. Because for this transistor to work, the collector emitter voltage should be at least equal to the base emitter voltage. So that's about 600 millivolts, but in saturation, it might go down a little slightly. So the output power is anywhere between VCC and ideally 0. And the active zone is between those two, between the edge of saturation and edge of cutoff. Why cutoff? Because there's no current. And if you look at this curve, isn't it interesting that the slope is negative? Or did you see it? Did you realize it? That it has a negative slope. And when we bias transistors or transistor circuits, we try to stay somewhere in the middle of this curve. Why in the middle? Because in order to work as an amplifier, the transistor first needs to be biased with DC voltages and currents. And then you can apply a very tiny AC voltage or current, millivolts to microvolts. And at the output, it's going to be amplified a few hundred times, maybe 1,000 times. So if you're in the middle over here, when you amplify the signal, the amplitude of the signal is going to be larger, right? And if it's not here in the middle, somewhere here, then you cannot go, mathematically you can, but physically you cannot go above VCC, even though you amplify the signal. So it might be clipped or distorted. So you want to stay somewhere in the middle. So if VCC is 10 volts, you'd like to stay around 5 volts here at the output so that you don't create a distortion of the signal. Am I clear? I hope so. Okay, now we've seen some designs like common base, common emitter, collector, but there are other circuits, and one of them is a differential pair. And differential pair or long tail circuit. Why it's called tailed, we'll see this in a little bit. But here is another thing that I would like to talk about today, and that's the current mirror. And I think we need to give a little break, like until past, and we'll continue after that, okay? All right. Kaçtı. Okay. Okay, ladies and gentlemen. How many are we? Some are not back yet. Okay, if you don't mind, I'll have a little cookie. Böyle ayıp oluyor, kusura bakmayın ama yani karnım acıkıyor. Tam şekerim fazla düşünce beyin umarım sizler bir şey yemişsinizdir. Öğle yemeği gibi. All right. So now we are going to be familiarized with this very symmetric circuit. And first of all, whatever you see here, what do you think it is? It's a current source, obviously. A DC current source. Okay. And these are Q1, Q2, Q1, Q2, Q3, Q4. These are 4 transistors, 2N plus PN, 2P plus NP. The actual differential pair is here. It's a totally symmetric circuit. And it's usually fabricated on the same chip so that these 2 transistors, Q1 and Q2, sometimes we call them T1, T2, whatever, they are fabricated on the same chip, so they are identical. And then here we have something slightly different. 2 transistors connected base to base. And then one of them, the base is shorted to the collector. So that means this transistor works like a diode. Since emitter base voltage is equal to emitter collector voltage. So it's working forward biased like a diode. Okay. What about this one? Here, we don't have the same short, but somehow we have the output on the collector or from the collector of Q2. If you look at the inputs are from the basis of the two transistors Q1 and Q2. And the output is from the collector of the second one. So since we have two inputs and one output, as you will know later on, this design, that part, works like a differential circuit or differential amplifier. What does that mean? Since there are two inputs connected to the two bases of the two transistors, that design amplifies the difference between the two inputs and provides it from the collector of the second transistor, or Q2. Q3 and Q4 actually constitute the current mirror. That mirror provides current to both these transistors in the differential pair in a quite interesting way. It's obvious that Q3 is forward biased as long as the voltage here at the collector of Q4 is large enough for this Q4 to stay in the active zone. The collector or emitter current of Q4 is exactly the same as Q3. That's why it's called a current mirror. So this part is called the current mirror. And the design says loaded differential pair. So this is a differential pair, and it's loaded with the current mirror. And this design, or the symbolic representation, can be another current mirror like this. Okay? So the whole circuit is something like this, actually. So we have, this is the current mirror. This time the current mirror is designed with the N plus PN transistors, but it has a biasing resistor and a load resistor. So loaded means you provide a resistor here, and it can also be a circuit. So current mirror loaded differential pair, the load is the load of the differential pair, and differential pair are these two transistors. And the difference between the current mirror and a differential pair is that you provide the inputs from the bases, whereas here, the bases are connected to each other and then shorted to the collector of one of them. So the current mirror is a totally symmetric circuit. Both BJTs are identical. HFE or beta, usually when I was teaching this class on the board, I preferred HFE. But now that we did the slides over the past 3 semesters, I'm using both HFE and beta. HFE actually means the hybrid parameter, that's H. F is forward, stays for forward. E stands for emitter. So the beta, or the current gain of the current mirror, is very, very high. We can even assume that the base currents could be neglected. It's so high. It's at least 100 or 200. And the base currents of the differential, not the differential pair, but also differential pair might be neglected. But for simple analysis, we may neglect the base currents of the current mirror. And as I said, the left or the first BJT works like a diode because collector and base are shorted. And the right one should be in the active mode, and that depends on the load. Oh, that rhymes. Anyway, so what is the current like? The current, according to this design, if we have two power supplies, a negative one and a positive one, and we cannot do Ohm's law or Kirchhoff's law over this transistor. We have to work with that one. Why? Because you can never know the collector base voltage. As long as it's in the active mode, you never know. You know that the base emitter voltage should be in the order of 600, 700 millivolts. But here, in this interesting design, the base and collector are shorted. So we know that the current flows over the bias resistor and over that short from the base to the emitter to the negative power supply. So the voltage drop on this biasing resistor is basically VCC minus VEE minus VBE divided by the biasing resistor. It can be simply changed by changing the biasing resistor. It can be made higher, can be made lower. And the differential pair or the long tail circuit is simply something like this. So you remember the Q1, Q2, and it hits Q3, Q4. Here, instead of Q3 and Q4, we have collector resistors. And so the total symmetry is more obvious right now, right? Do you agree? And for biasing purposes, we usually assume that the bases are connected to ground, but at DC. At AC, the inputs are provided from the two bases and the outputs might be individually from the two collectors or differentially between the two collectors. So it might have differential gain or of the differential output, differential gain. It can be used in different ways. So amplifies an AC signal difference between the two bases. Q1 and Q2 are identical. The design is totally symmetric. Instead of this DC current supply, it can also be biased with a resistor like RE. So in that case, when you have an RE over here, the other end of RE should be probably connected to a negative power supply. Why negative? Because the bases for biasing purposes are connected to ground. So if you provide a resistor here and connect the other end of the resistor to the ground, and there is no voltage difference, you cannot basically bias the circuit. Okay, at rest, both bases are grounded for DC analysis, and that we call biasing. So these two emitter currents, or the sum of them, is equal to this I. And if the beta is very high, then it can be assumed that that current is equal to the sum of the two collector currents. In that case, the collector current And by biasing, we usually mean we want to find the collector current and the collector emitter voltages or collector voltages, depending on the case. So the collector current is then when we go between the ground, VBE, a resistor here, the other end of the resistor connected to minus VEE, then the voltage drop on the resistor is between the ground, minus VBE, and minus VEE. That means VEE minus VBE divided by 2RE would give you the collector current. So what I'm going to talk about is this much so far. So your copy or cheat sheet, prepare a good one for yourself, but it has to be your handwriting and no printout or photocopy, because I know that as you are preparing that copy sheet, you are going to learn. And if it's somebody else's copy sheet and you basically photocopy it, you're going to deal with someone else's mind. But your mind is for yourself. The other person's or friend's mind is for himself or herself. Excel, well, that was, I'm not sure that you can use Excel on your cell phones, but if you don't have a calculator, you might use Excel on your cell phones, but no laptops or tablets are allowed. Just bring yourself and careful with units. I'm saying this many times. I hope this year you are better prepared. And so, yes, this is the end for me. And now Beck is going to solve some problems, or a problem, I assume, right? A problem with many sections. Okay. Evet efendim. Şimdi bir bölüm yapmıştık geçen hafta. Ya öyle mi yapmıştık?
Evet. Bilgisayarınızın sesi.
Neden?
Bilgisayarınızın sesini.
Ha, hemen. Şey buradan kapatayım ben. Direkt kapatayım. Kapattın mı? Tamam.
Dışarıda